Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Welcome to another module of the Design Patterns training. My name is Martin Schroeder at swedishembedded.com. If you have any questions regarding this training, you can always join our Discord channel at swedishembedded.com, or you can email me directly at martin.schroeder@swedishembedded.com. In this module, we're going to look at the conditional variable pattern and how we actually implement this in code. And this pattern is primarily designed to provide a way of notifying multiple threads, one or more threads, about an event, so that all the waiting threads can be awakened at the same time, and so that we have proper synchronization with corresponding mutex. So we're going to look at how we use a mutex in conjunction with this pattern, and how we ensure complete mutual exclusion between all of those threads that are waiting for the event and the data that actually comes with the event. So let's get started. The conditional variable pattern consists of three main operations. We have the wait, the signal, and the broadcast. And any threads that are waiting for a conditional event are going to call the wait function, which will, they're going to first lock a mutex, which is responsible for mutual exclusion for a data structure that is shared between multiple threads. And then it's going to call the wait operation, and the wait operation is actually going to atomically unlock the mutex and place the current thread on the wait queue. So this unlock operation and placing the thread, swapping out the thread, is done atomically, so the pattern itself guarantees that we can keep the mutex unlocked while we're waiting for the event, and there wouldn't be any race conditions between threads at that point. We have guarantees about the mutex being locked, so we're going to look at how this actually works in practice. We're going to have a mutex that we're going to lock at first. We're then going to go waiting for the event, and the mutex is going to be unlocked while we're waiting. And then when the event arrives, the mutex is going to be locked again. And when we exit from the wait function, we're going to continue with the mutex locked. So now we can access shared data that is shared between threads, and we can check for the actual condition to be true that we are waiting for. So we can use the conditional variable to signal that something has changed, and then we're going to have to check for the condition manually that it actually is what we expect it to be, and then we can continue. And then we're going to unlock the mutex at the end, ending the critical section that is protected by the mutex. Another thing that the conditional variable pattern allows us to do is to wake up multiple threads simultaneously. So we can potentially have multiple threads awakened at the same time atomically without any potential interruption in between. And all of those threads are going to then continue and try to acquire the mutex at the same time. So as soon as the mutex becomes available, the next thread is going to be able to continue. And we usually check conditional variable in a loop, because we can wake up for a variety of reasons, and it's not necessarily the reason that we are waiting for. So we use the conditional variable to check for complex conditions and arbitrary conditions. So we can have, for example, a simple flag, or we can have a number of methods that need to be called to check for the condition. So we can have, for example, more complex conditions that need I/O access and maybe talking to some device that is connected to our board, and the conditional variable pattern gives us the means to do that. We use the conditional pattern for three main purposes. So number one is signaling multiple threads. So we can have a broadcast event that signals multiple threads that something has happened. We can use it for waiting for multiple complex conditions that need to be true in order for us to continue. And we can also use it to implement producer-consumer patterns. So we can have a number of items that we push to a queue, and then we signal threads that the items have been fully pushed, and then the threads wake up, process the items, and in this way we can implement a producer-consumer pattern in a much easier way. The benefits of this pattern compared to other synchronization primitives is that this pattern is explicitly designed for arbitrary conditions. So we store the condition either as part of the data that is protected by the mutex, or even we can have dynamic conditions that we retrieve using function calls. So we can call a device, we can retrieve some register value and check for the condition in that way. So we have arbitrary conditions. And the mutex that is guarding concurrent access to this shared data or to whatever device that we are sharing between threads, this mutex is always unlocked while we're waiting. And this unlock happens also in a very safe way. There can't be any race condition with regards to this unlocking because we have a spin lock that protects that area. So we always unlock the mutex and queue the thread as an atomic operation. But the mutex is always unlocked while we're waiting for the condition, so other threads can potentially lock the mutex, do something to the data, and as long as the conditional variable is not signaled, our thread will still continue to wait for the event to happen. And another valuable thing about conditional variables is that they can be used from interrupt handlers. So they're very similar in that sense to a semaphore. We're not actually locking the mutex or doing any mutex operations from interrupt handler. We're simply waking up the threads. And it is the mutex locking operation actually happens in the thread context. So it's perfectly fine to signal a conditional variable from an interrupt handler. And this can be a way to broadcast an interrupt event to multiple other threads that are maybe waiting for this interrupt event. And a very simple example could be waiting for vertical sync event on a display where you might get a pulse on an interrupt signaling vertical sync. And then let's say you want to have multiple threads synchronize into that vertical sync. So they would all be basically waiting for the conditional variable. And then when the vertical sync occurs, you would do a broadcast and wake up all of those threads at the same time. The drawbacks of the conditional pattern is that it's more complex to use. So you have this mutex that you need to take care of. There is a specific pattern for waiting for the condition. You have to do it in a loop. So it's a little bit more complex, but once you understand how it's implemented, it's hopefully going to be very easy for you to understand how to use it. Number two is it consumes more memory because there's always at least one other mutex that you're going to be using. So you need to have basically a mutex per thread that each thread is going to use as a way of guarding this critical section. And that adds additional memory usage to the application. But usually that's not a big issue. It's simply usually you would have those mutexes anyway because the data structures you're accessing are going to be shared anyway. Next, let's have a look at the implementation. So I'm going to walk you through the implementation of the conditional variable of each one of these methods. We have the wait method. This operation is going to wait for the signal to arrive. We have the signal method, which is going to wake up just one thread at a time. And we're going to have the broadcast method that is going to wake up all of the threads at the same time and then do a reschedule and do this operation atomically. So not one at a time, but all of them at a time and then doing a reschedule after that. The implementation is really pretty simple. The main use case scenario we're going to look at is would look something like this. So we have a context. We have a mutex that is used to lock this, to ensure mutual access to this context by multiple threads. We have a condition. Let's say in this case, we can have a simple Boolean flag that signals the status of the condition. And then we have our conditional variable. So it is this conditional variable we're going to be signaling, and we're going to use this mutex to guard this data structure, and we're going to use this data as the meaning of our event. So how do we actually use it? Okay, so let's say we want to wait for ready to become true. This can be arbitrary complex condition. Remember, this doesn't have to be a simple variable. It can be arbitrary condition. So we want to wait for this condition to be true. We'll implement it like this. So we're going to lock the mutex first so that we get mutual access to this data structure. We're then going to loop until or while this ready flag has not been set. So when we check the status of this flag, we have the mutex locked, so there is mutual exclusion guaranteed with respect to other threads. And if this condition is still false, then we're going to execute convar wait, and we're going to pass the conditional variable, and then we're going to pass also this mutex and a timeout. And the reason we pass the mutex is that what will happen here is that this method call is going to first lock a spin lock, making sure that that is basically safe against other CPUs and interrupts. And then it's going to unlock the mutex, and it's going to queue our thread in the queue for this conditional variable. So when we execute this method, we're always going to be suspended, and the CPU can either go to sleep or another thread can run. But our current thread is going to be always suspended when we call this, and then it's going to be waiting for the appropriate signal on this conditional variable. And once we return from this function, the mutex is again guaranteed to be locked. So we can then go back to this loop and we can check the condition again. Let's say the condition is still false, we go back to sleep. If the condition, and basically what we can do here is we can set a timeout. So that we check for the condition, we wake up with some timeout, maybe we do some other work here, and then we check for the condition, we go back to sleep. And when the condition is true, remember the mutex is still locked, so then we unlock the mutex, and now we're done with waiting for this particular event. So now we know that this condition is true, we can continue and do whatever else we need to do in response to this condition becoming true. And when it comes to signaling this condition, what we do is we can basically call convar broadcast. Now, if there is some data that we need to modify as part of the condition, then we want to lock the mutex again. But we don't strictly need to lock the mutex just to broadcast the conditional variable, because there is nothing in the conditional variable that requires this mutex to be locked when we broadcast. But if we are doing this from a thread, then we can lock the mutex, we can modify the data, and then we can unlock again after we have broadcasted the condition. But if we are doing it from an interrupt, then we would just basically call con broadcast, and that would mean that the interrupt has occurred, and now we just want to wake up some threads that are waiting for this interrupt to occur. So this is a good way to broadcast an event to multiple threads from interrupt context and then to the thread context. So the threads can continue in their own respective thread context with their shared data guarded by the mutex. The wait function is very simple. So the only thing we do here basically is we lock this spin lock. We then unlock the mutex. So now this section is done atomically. It cannot be interrupted by anything else. We then always pend our current thread. So we always put our thread to sleep, and we provide a timeout here for when it's going to wake up again. So the thread can potentially wake up even after the timeout expires. It doesn't need to wake up specifically when it's being signaled. And then we, once this function returns, so this function can only return when the thread has been awakened again. So once the thread has been awakened again, then we lock the mutex again, and then we return. So when we return from convar wait, the mutex is guaranteed to be locked again. And when we want to signal a conditional variable, we have a special method called Convar Signal. And this method basically takes one thread from the wait queue, and if the thread is not null, so basically there is a thread to wake up, then we ready that thread and we reschedule, passing the spin lock. Remember the standard way of first we lock the spin lock here, then we pass this lock to the reschedule, and then reschedule unlocks it for us when our current thread has been rescheduled. And if there is no thread waiting, then we simply unlock the spin lock and we return. So this is a very lightweight operation, especially if there's no thread waiting. We just unlock the signal and we return. And you can see here that there is no internal counter like with a semaphore. If there is no threads waiting, then nothing is done. Basically, this function basically does nothing. And if new threads arrive and wait for this conditional variable, then they will continue waiting until another signal arrives or until they wake up because they have timed out. And now we have another function called broadcast, and the broadcast function locks the spin lock just the same, but what it does then is that it loops through all of the threads that are currently queuing, and it readies them first, and then it calls reschedule. So it readies the threads, all of them at once, and this operation cannot be interrupted, of course. And then once they are all marked as ready, then we reschedule, and then one or more threads continue depending on how many CPUs you have, and then they all contend for the same mutex. So if you look here, they will all wake up here and they will try to acquire the mutex. So now it's the mutex logic that is responsible for which thread is going to run first. So that's it, and that's really the simplicity of conditional variables, but it gives us this ability to signal something from an interrupt to multiple threads all at once. So best practices for using conditional variables. Don't use them very often. There is often no need to signal things using a conditional variable. Often it's very sufficient to use a semaphore and just signal one thread. But if you have the specific requirement that you need to signal multiple threads at once, then the conditional variable is really the pattern that's been designed for that kind of purpose. And always check the condition in a loop, because you can never be sure that a particular condition is true. Even if you have only one place to begin with, where you set the condition to true and then you signal your conditional variable, you still need to check for that condition to be true, to be completely sure that it's actually true. Because let's say you add another place where you signal the condition, and maybe you're modifying a different variable or setting a signal in a different condition, then your original code will break. So in order to avoid this kind of breakage, you should always check for sure that the condition has actually been met when you wake up. And the main common pitfall is, of course, that you wake up for some other reason. So for example, on Linux systems, you can wake up because your program has received a signal, or there's a variety of reasons why you can essentially wake up from a condition variable while you're waiting for a condition variable. And so the spurious wake-ups, you really should be aware of this, and this is why you also need to check for the condition explicitly before you continue. The main alternatives to conditional variables, number one is the semaphore. So if you want to signal from an interrupt to one other thread, you can use a semaphore. Another alternative is work queues. So you can always schedule a work item to run in thread context. So if you need to do something that you need, let's say you need to do something that cannot be done in an interrupt context, and you need to do it in thread context. So maybe you're thinking that, okay, I can use a conditional variable, I can wait for the interrupt to occur, and then I can do my work that I need to do. But in many cases, it's actually sufficient to simply submit a work queue item, and the system work queue will then execute that item in the context of the system work queue thread. So in that way, you can defer work to thread context without having to create a separate thread. So it's very useful work queue item. And the third alternative is the event bus. So event bus is another pattern that implements the publish subscribe mechanism and gives you ability to emit events to which many other subscribers can potentially subscribe. So in this way, it's similar to how we broadcast through a conditional variable, but the conditional variable is a very lightweight method of doing this and doesn't require a complex infrastructure for events. The conditional variable makes this very simple, but has its own limitations in terms of like subscribing to multiple topics and things like that. But nonetheless, event bus pattern is also an alternative to this broadcasting operation that the conditional variable allows you to do. So we've looked at the conditional variable. It combines two concepts that we covered before, the spin lock and the mutex. And you can see how all of these concepts build on each other, and they have their own specific uses. And when you understand the synchronization concepts, it becomes very intuitive for you to know what happens when you see other people use these concepts in embedded programming. So I hope you learned something. I hope this was an interesting introduction to synchronization primitives and the patterns that we use for synchronization. Let's check your understanding of this module before we continue. So a quick quiz on conditional variables. Can a conditional variable be signaled from an interrupt handler? When a conditional variable broadcast method is used, at what point do all the threads wake up and in what order do they continue after this broadcast if there is only one CPU? So remember the mutex pattern. How does the mutex pattern decide which thread is going to run next? If there are multiple CPUs and broadcast is used to signal a conditional variable, can a thread be swapped in and start running before all of the threads have been woken up? What is the main difference between conditional variable pattern and the semaphore pattern? And one of the things that is actually different is that the conditional variable wait function is always going to wait. It's not going to, it's not a cheap operation in some cases, like with a semaphore. It's always actually going to swap out your thread and put it on the queue. So it's always a context switch involved. If multiple threads are waiting for a conditional variable, which one will be chosen to run first if the conditional variable is signaled and not broadcasted? So which one will be chosen to run first? Why is it always important to check the condition itself in a loop, even if you know that you're only signaling when a desired condition is true? If you don't do this, when will it cause you trouble? All right, that's it for this module. I hope you learned something, and I hope this was useful.